Hello, everybody. Before we begin, let me introduce myself briefly. I'm Guillermo Rivera Alfaro. I'm a sophomore, and my major is electrical engineering. Today, I'm going to be solving one of the three problems for the final exam of the lecture application of mathematical software. First, I will begin by explaining the problem itself, and then I will attempt to solve this problem first algebraically and then by using Python. Finally, I will briefly discuss the difference between the solutions. The problem I decided to solve is problem number 2. It's a physics problem and it goes as follows. A projectile is launched at 0 with velocity v at the angle theta to the horizontal. The parametric equations of the trajectory are x equals v cosine of theta times t and y equals minus 1/2 of g t squared plus b sine of theta times t, where t is the time measured from the instant of launch and g represents the gravitational acceleration. If the projectile is to hit the target A here at the 45 angle shown in the figure, determine v, theta, and the time of flight. Okay, I will explain this problem more in detail and how we can solve it. First, I would like to highlight that we're dealing with a parabolic motion or projectile motion. We can deduce this by the equations that describe the movement of the projectile. As you can see, x depends of t linearly and y depends of t by the square of t. Also here, x represents the horizontal distance and y represents the position along the vertical axis, x and y here. We also have important data, as we can see in the picture. We know the height and the horizontal position of the projectile at a certain moment. At certain time t, the projectile is going to be here at x equals 300 meters and y equals 61 meters. Also, we know that the angle at that moment is 45 degrees. Well, however, we only have two equations and three variables, v, theta, and t. We need another equation for us to solve this problem properly. We know that due to the properties of the parabola, the movement in x is going to be constant. The velocity in x is going to be constant throughout the project, the movement. And y is going to change thanks to gravity. So if we know that y, the velocity in y is going to change according to time, maybe we can use this equation here and we can find how the velocity behaves as a function of time. Okay guys, so let us start by drawing the motion of the projectile again. We're gonna have something like this, where here this distance will be 61 meters and here will be 300 meters and the angle here will be 45 degrees. We already have these equations, x equals v cosine of theta times t and y equals v0 sine of theta times t minus 1/2 of g t squared. Okay? And also we were talking about that we need another equation and we can derive that equation from here, the position. We know that the velocity is given by this equation here. So maybe we can try to take the derivative of that equation and find the velocity. So for this part, we're gonna only have v sine of theta, and for this part, this 2 goes down, multiplies 1/2, and give us gt. So now we have how the velocity behaves along the vertical axis. But now we have to know how it behaves at this point. Well, we know that in this point, the projectile is going down, so we know that the velocity at that point will be negative. And if we draw the vector at that point, we're going to have something like this, 45 degrees here and also 45 degrees here. Therefore, at this point, we can find the velocity in y as follows. By finding the component along the vertical axis. Thus, we can write the three equations as follows. X equals v cosine of theta t this one that was given by the problem 2, and also this one. Sinus 45 degrees equals V0 sine of theta minus GT. Okay? And there we go. So now let us try solving this algebraically first. This might seem a little bit convoluted because we have 3 equations, and at some point the 3 variables are not linearly proportional to each other. Instead, they're like multiplying each other, so it's not that easy to solve it like mathematically, algebraically. But let us like give it a shot. Let's see. So we know that the velocity can be written as follows. By using the third equation here, let us label this one the second and this one is the first equation. Thus, we can also find t from the first equation as follows. And now we can like maybe combine these 2 equations and find how the velocity behaves, and then substitute in another equation. So we get that this v is gonna multiply this v later, so we're gonna have v squared equals gx over cosine of theta times sine alpha plus sine theta. Okay, maybe let us try now substituting this equation on the second one, and we're gonna get the following equation: v0 sine of theta, and then we can use this one here. So we're gonna obtain the following result. And t squared will be given by this cosine squared of theta. Okay, now let us simplify this a little bit here. We can like simplify here, and maybe this v sub 0 squared we can like substitute it by using this one here. Let us try that. So we're gonna have sine divided by cosine times x minus 1/2 g x squared divided by cosine squared times cosine theta sine alpha plus sine theta divided by gx. So this one can cancel here, and this one here, and this one here too. Also, alpha is 45 degrees. I just wrote it as alpha to simplify the problem, and not to mention 45 degrees every time. So after a little bit of algebra, we can like multiply cosine here and here and here, and we're gonna obtain the following result. And also by 2. 2y cosine of theta equals 2x sine of theta minus x sine of alpha plus sine of theta. And a little bit more of simplification, we're gonna get 2y cosine of theta equals x sine of theta minus x sine of alpha. Well, at this point, we know what is gonna be the value of y and the value of x. We know the value of alpha too. The only thing we don't know is theta here. However, this equation is not that easy to be solved. So after like plugging this equation in the calculator, I got the following result. Theta equals 1.1 rad, or 63.02 degrees. And then if I know this value, I can find the velocity by using this equation here. So let us go back. V sub 0 will be the root of gx divided by cosine of theta sine theta plus sine alpha. And this will be 63.68 meters per second, a really high velocity. And finally, we can use again this equation, t equals x divided by v sub 0 cosine of theta as the one we had here, and this is 10.38 seconds. So now we have found the values algebraically. It wasn't that easy. Actually, I had to use a calculator to find the values. I couldn't solve it like algebraically that easily. So let's try this by using Python now. Thank you. Now let us solve this problem by using Python. We'll use the library SciPy, where we can find a command that solves nonlinear equations. Here, scipy.optimize.fsolve is a great tool for this. As the description says, it returns the root of the nonlinear equations after we give a vector valued function that equals 0, as you can see here. So after knowing that, let us try implementing this using the data we have gathered before. We have the equations here and the values. After plugging these values onto these equations, we get a nonlinear system of equations. Here f represents our vector valued function that equals 0, and x0, x1, and x2 represents the time, the angle, and the velocity respectively. I would like to emphasize that v and t are multiplying here all the time, so in order for us to not get a wrong result, I divided everything by t, which is x0 here. Because, for example, if both of the values are positive or both of the values are negative, we're going to get the same result for x, y, and in this equation as well. So in order to avoid that, we're going to make these variables not to multiply each other. Okay, so let us first call the optimize function here that we're going to use to solve the nonlinear system of equations. Then let us call numpy, let us import the math library, and let us import pi from that library as well. So as I told you before, we're going to call this function here so we can get this result and then implementing in the optimize function. So by plugging these values here and then later calling the optimize function, we're going to get an array of the variables. And we're going to save those variables as t for time, angle, and v for velocity. However, although this value looks a little bit funky, since cosine and sine are periodic functions, we can get the same result out of this. So the time of flight will be t, which is 10.39 seconds. And then here, for us to find the angle, first what I did is to find the cosine of the angle, and then the arc cosine of the angle, so we can have the angle back, but now with the minimum value, not this funky value that we had before. Later, I called the math.decrease function so we can find how much is in decrease. After implementing that, we get that the decrease are 63.05. And finally, the velocity will be 63.70 meters per second. The overall code looks like this. So for us to solve the problem, it only took 3 lines, 1, 2, 3, where we call the libraries, implemented the function, and use the optimize command. Then another 3 lines only to find the values and solve the problem that was given to us. So to wrap up, we solve a physics problem algebraically and by using Python. In both we obtained the same results. The problem solved algebraically took us a lot of time and led us to a trigonometric equation not easy to solve using conventional methods. Whereas by using Python, we save a lot of time and it wasn't computationally expensive to solve neither. Well, that was my final exam. Thank you everybody for watching. Thank you.